Alright, let's now cover the popular self-attention mechanism used in transformers. And we will start with a basic version of that and introduce the additional details in upcoming videos. So one thing I should mention first is that transformers are solely based on self-attention, and in contrast to RNNs, no recurrence is required. Yeah, and again, as we've seen in the previous video, attention is used to create these context-aware embedding vectors. Context-aware here means that we model the dependencies of the current input with respect to all the other inputs. So let's take a look at an example. So here we have a context-aware embedding vector at one time step. And if we suppose that the time step is 2, then this is the context-aware embedding vector corresponding to the second input word here. And like before, the values alpha here, they represent the attention scores. So notice here that we are multiplying these inputs x with the alpha, the attention scores, to obtain the context-aware embedding vector z. So z here is essentially a weighted sum over the inputs weighted by the attention scores. So now that we have seen how we compute these context-aware embedding vectors using the attention scores, let's actually dive in and see how we compute the attention scores themselves using a basic form of self-attention. So we start by computing a similarity score omega between each ith element and all the other input elements. So here omega ij is the dot product between the ith input element and the jth input element. And the dot product here is essentially quantifying how similar the vectors are. And then we take this unnormalized attention score, the omega, and normalize it using the softmax function. So the softmax function here is used as a convention so that all the attention scores sum up to 1. Since this was very technical and very complicated, let's actually go through it step by step using an illustration. So here's an illustration of how the computation of the unnormalized attention scores look like. So suppose we take the ith input element. For simplicity, maybe think of it as a second input element. And what we do is we take this input element and compute the dot product to each other input element. So as a result, we obtain these different unnormalized attention scores. And then once we have all these attention scores, we can use the softmax function to get the normalized attention scores that sum up to 1. And then once we have these normalized attention scores, we compute the weighted sum by multiplying each attention score with a corresponding input to obtain the context vector. So this context vector here will be very specific to the ith input element because the attention scores themselves are specific to that input element as well when we compute the dot products. Yeah, and this is in a nutshell how the simple, basic self-attention mechanism works. However, notice that this self-attention mechanism does not have any learnable weights. So there's nothing that can be learned during backpropagation or the neural network training. So in the next video, we will then introduce the real self-attention mechanism with the learnable weights.